So hi everyone, my name is Mark, I'm from GSS and I'm going to be telling you about how you can achieve the lowest power consumption of CO2 sensing with our devices. I'll give you a quick intro to GSS, who we are and what we do, how we measure CO2 with our devices, and why we've chosen to use LEDs. I'll also go through the method of calculating the power consumption and also other strategies for reducing the power consumption using different modes in our sensors. And then finally, I'll give you an introduction to CozIR Blink, which is the lowest power CO2 sensor that we have. A little bit of housekeeping to start with. So there'll be an online chat function you can see that is being moderated by my colleague Lauren, and she will take all the questions at the end and we'll come back to you with a response after the presentation. And you can ask anything at all about anything that's happened in the presentation. Then a follow-up email will be sent within 24 hours, and this will include the slides for today as well as a recording. There'll also be a small feedback survey that should only take a couple of minutes to fill in. If you could fill that in, that would be much appreciated. Who are we? Who are GSS? So we design and manufacture solid-state NDIR CO2 sensors. They're all designed and built in-house at GSS. We have our own in-house MBE LED and photodiode growth facility that uses our own proprietary LED-based systems. And we also have a very agile in-house R&D team, which gives us a lot of flexibility in custom sensor designs as well as the standard off-the-shelf products. How does a CO2 sensor work? Well, for our systems, we have 4 primary functions. The first of which is our mid-IR LED, which we make on site. This transmits an infrared beam, which passes through an optical chamber, which contains the CO2 gas, which is then detected by a photodiode detector, which we also make in-house. The data is then transferred out to a microcontroller to be analysed and read out. Now, the reason we use an LED is because the absorption band of CO2 is centered around 4.25. So we can accurately grow LEDs to transmit a narrow bandwidth that fits very nicely inside that absorption band that you can see there. And by Beer-Lambert law, we know that the concentration of the CO2 gas is directly related to the attenuated or the transmitted signal, and also the length of the measurement chamber. So why LEDs? Well, typically they have longer component lifetimes, more efficient spectral overlaps with the gas, as I've just said, and also the measurement rate is much faster than typical incandescent sources. The measurement rate can be as fast as 50 Hertz from our Sprinter R product. LEDs typically minimize the consumption of a sensor, and we can reduce that further by running the LEDs pulsed rather than in constant wave operation. And because of this, we've seen that our sensors being used in a lot of battery optimized applications with some really good results. So how do we calculate power consumption? So the power consumption here, we show the current consumption, which is measured with a high-sided differential op-amp. And we can see that there are different stages in the sensor's operation that use power in different quantities. Here we have sleep mode, which is right down almost zero, I think 0.03 milliwatts or 0.01 milliamps is the sort of what you would put it into to save power. And then when you send a command to wake the sensor up, it comes into the wake up phase. There's a small peak where all the electronics fire up, the capacitors start filling, and then it drops down into a kind of quiescent state. And then the measurement phase here, where the LEDs are firing and the photodiode detector is picking up the transmitted signal. you can see there's a small peak here. And then we get to the data processing phase and the data transmission phase, where the data is then analysed and transmitted out to the user's system. Then the system is returned back into sleep over the course of the next few hundred milliseconds. Now, the time scale, this is a zoomed in graph, so the time scale here is 50 milliseconds. The measurement cycle of a typical device is 500 milliseconds, which we can see here, so half a second. Every half a second, a measurement will be taken. And you can see that same graph zoomed out here with the same peaks. Now, if we integrate the power consumption over discrete intervals, and the measurement interval here was 20 microseconds, we can then calculate the total energy consumed during each 500 millisecond measurement phase. For the typical devices in the CozIR and the CozlR range, where the measurement rate is 2 per second, we can calculate that the energy is 1.56 per measurement, and that gives an average power in the active state of 3.12 milliwatts. So how can we calculate the power consumption in the real world? So generally, people wouldn't just have the sensors running 100% of the time. What people typically do is choose a situation where the sensor is mostly asleep, consuming very little power, and then wake the sensor up to take measurements when they need to. So we can actually calculate the power consumption based on these parameters. So we have this equation here to calculate the average power consumption, where you take the E measurement, which is 1.56, so that's the measurement energy for one measurement. That's what we've just calculated in the previous slide. N, that would be the number of measurements you would like to choose every time you wake up the sensor. P sleep is how much the sensors consume when they're in sleep mode, which we know is 0.03 milliwatts, so that's been measured. T period is the time between each set of N measurements, so basically every time, the time between waking up. And T measure is the time required for a single measurement. So for most of our sensors in the CozlR and CozIR range, that's 0.5 seconds, but it's faster for the Sprinter range. Now, a quick example of this would be, say you wanted to wake up the sensor every 2 hours and take 16 measurements. We already know that E measure is 1.56, N would be 16, P sleep 0.03 milliwatts, T period is 7,200 seconds, that would be 2 hours, and T measure, as we know for CozIR and CozlR, is 0.5 seconds. This would give us an average power of 33.4 microwatts. There are additional strategies that you can employ for reducing the power, and this is done by choosing different modes for the sensor. So the K0 command, K1 and K2 are all UART modes. So if you're using a UART sensor, K0 would be putting the sensor to sleep. So essentially what we've just covered in the past few slides. To save power, you would put the sensor to sleep when you're not using it. K1 streaming mode is the constant measurement, constant data output. So that's the maximum energy that you would use. K2 polling, the LEDs are still firing and the measurements are still being made, but the data is not being read out or analysed until you poll the sensor. Now, during the polling phase, you can typically make a modest saving of about 0.5 milliwatts, which is similar in I2C mode because there is no streaming, constant streaming for the K1 for I2C. So you have to pull the data. So straight away, you're making modest savings of about 0.5 milliwatts. Now, there is a much better way to save energy, and that is to use our lowest power sensor, the CozIR Blink. So this sensor is unique here because it's designed to be completely powered down after a set of measurements. So instead of using 0.03 milliwatts, you're using basically zero power. The CozIR Blink will take a set of measurements and it will produce a single averaged CO2 reading based on that number of measurements. and then it will automatically go into a sleep mode. The measurement is held in the memory and all the other functions are stopped. At this point, once you've read the data out, the CozIR Blink is ready to be powered down completely. So how can we calculate the power consumption of the CozIR Blink? So the default setting is to wake up and take 16 measurements and generate a single CO2 reading. You can see on this graph here that the sensor wakes up, there's that initial spike, but then the subsequent spikes are much lower because the electronics are never fully powering down in between measurements here. And this full measurement cycle here of 16 measurement takes around about 3.5 seconds, at which point the data is read out and the unit can be powered down. So we have a simplified equation based on the equation we've shown a few slides ago, but because we don't have any power consumed during the off period, we can simplify it right down to what we see here, where again, n is the number of measurements. This time, your choice is between one single measurement and 32. 32 is chosen because beyond that, within 3.5 seconds, you're looking at putting a thermal load into the device that's really not suitable. So E measure, again, is 1.56, as in all sensors. And if you're taking 16 measurements every 2 hours, this would result in 3.47 microwatts. Now, taking one measurement every 2 hours would be 0.22 microwatts. But what does that actually look like? So with a AA battery, about 2 amp hours, and a CozIR Blink running at one measurement every 2 hours, the theoretical calculation would be well over 3,000 year battery life. Now, we're not saying that in 3,000 years' time, when an archaeologist unveils an ancient GSS sensor, it'll still be running on one battery. Of course it won't. First of all, the device lifetime is orders of magnitude lower than that, plus all the external factors that cause batteries to drain. But what we are saying is that we're confident that with a CozIR Blink, you have the best chance of achieving the lowest power consumption possible. To conclude, we can help you optimize your system for power consumption when you're measuring CO2. And the CozIR Blink gives you the best chance of doing this. So our sensors, with an optimized design and careful consideration of the parameters, you can achieve the longest battery life possible in your system. Thank you everyone for listening. I hope you have a great day.